But then we stopped at this point where we said or asked, what if, just a what if question, if I took the sum of these two fields E of t minus tau and produced an intermediate electromagnetic signal which oscillates at frequencies similar to that of the incident pulses themselves, right. But this intermediate signal is dependent on the square of the sum of these two inputs. This is not the signal that the slow or infinitely slow detector measures. The infinitely slow detector will measure a signal which is linearly proportional to the left hand side, where we have something of an I of tau. Okay. If this is also an electric field, what is in the integrand, and the detector is asked to measure this, the detector will faithfully absolute value square this, integrate this entire content over infinite time, and then produce an output. Okay. And this output can be produced for every delay value of the arrangement in the interferometer. If we begin with a signal which is or an electromagnetic intermediate wave which is quadratic in the sum of these two, then the autocorrelation is said to be of the second order. So, is this possible in the lab? I think I sort of let the cat out of the bag in the previous lecture. We will come back to this in greater detail now. Yes, indeed it is possible, but it is not only possible to do this to the second order, we can do this to the third, fourth, fifth, nth order too. Okay, so it could be done to any order provided we have the means for it, right. But first, a first order autocorrelation signal typically looks sort of like this. It has an envelope, the entire thing is riding on a DC, which is the absolute value square of E of t plus absolute value square, the integral over the absolute value square of what we earlier called E of t integrated over sufficiently long time, which was from the signal from arm 1 or the pulse from arm 1, likewise the pulse from arm 2. So, there will always be some signal at your detector. But what you are interested in is this temporal variation in the region where the pulses temporally start overlapping. Okay. So, this is the first order autocorrelation signal typically, which I liberally borrowed from the example given in Roulier's book, where an 800 nanometer 100 femtosecond pulse is incident. So, here we have made simplistic assumptions, but also in a real life, this is a real life measurement. So, the pulse is close to Gaussian in time, has a full width at half max of about 100 femtoseconds. All this goes into making this picture. Then for every point of delay, you scan this delay all the way from, you can say, plus 150 femtoseconds, which is essentially 2L by C. Okay, the delay tau is 2L by C. So, vary the L, right. I said that 300 nanometers is 1 femtosecond, right, or 300 micrometers is 1 picosecond, right. So, figure out yourself what the time step values would be, scan this and you would be able to get such data. And as I brought up in the previous lecture, this full width at half max, the tau of the autocorrelation is linearly related to the tau of the pulse. So, at least this we will be able to figure out, provided we have some knowledge about the shape of the envelope of the pulse. We need to make some reasonable assumption. It is Gaussian, it is secant hyperbolic. It is approximate information, but you can ask if it is an ab initio metrology, I do not even know what the envelope of the pulse is, I know very little about the source, then what do I do? Very good question. So, that is precisely the point. If we do just autocorrelation, we are going to get some partial information about the pulse, and we may choose to live with that, although as the saying goes, it would be a dangerous thing to live by and bet upon always. It is very partial knowledge. So, in order to improve things, right, what can we do? One way is to say, hey, why only first? Let us measure the second order autocorrelation too. How do we do that? Yes, that brings us some hope. We will understand better as to what we are doing in the first, second, third and higher orders of autocorrelation. Now, instead of measuring the sum of what did we have earlier? So, first order, the signal essentially came from an infinite integral of dt. This is the operator if you so wish, into which we put in E1 of t plus E2 of t minus tau, where tau is the delay, right. So, now here the next idea is to stick in E1 of t plus E2 of t minus tau. This could even be the absolute value square of this guy. The second order signal would essentially be consider the absolute value square of this entire thing, integrate this from infinitely. That would be the second order signal. But how do I generate a signal proportional, linearly proportional to the square of this sum? How do we do that? Right, remember E1 and E2, I missed the 2 there, are merely copies of coherent identical copies of the pulse itself created by a beam splitter in the setup. How do we generate that? Well, we can generate this by using a second harmonic generation crystal, whereby you focus these two pulses coming along different paths, and the second harmonic crystal generates a signal oscillating at twice omega, if omega is the oscillation frequency of the incident pulses, which is epsilon naught chi 2 E1 of omega E2 of omega. So, this, or rather I should, why do I even say E1 E2? It generates this signal. So, now if the sum, if here E of omega is the sum of these two fields, coherent sum of these two fields, remember for every step of the delay stage omega is fixed, it is not constant, it is a parameter you vary, you turn a knob on the omega, you fix it. So, for every omega you can consider an electric field, and this goes into this equation which makes things quadratic. Now, the question obviously comes from the output of this crystal, you have 3 signals or 3 electromagnetic waves coming up, 1, 2, 2 of the beams intersected in this crystal and it produced a field. Third, you have the 2 omega field. Remember I told you that this a plain vanilla detector is not a spectrometer. So, if I just stick a detector in, the detector will faithfully measure or give a response of all the electromagnetic signal that is incident on it. Okay. I am assuming here that the detector is sensitive to both omega and 2 omega, which usually tends to be the case, or you can be clever and buy a detector which will only detect the second harmonic signal, which is also what sometimes is done, but keep that as an aside. But the point being that in order to do second order autocorrelation, you want to measure only the second harmonic on the detector as a function of the delay tau. If you do that and vary the delay, you get a second order autocorrelation. And no surprise, if you replace this with a third harmonic crystal and measure the third harmonic alone on the detector as a function of delay, you would end up doing third order autocorrelation. Okay. So, this intensity autocorrelation, let us call this A2 of tau. Okay. So, you can get a signal out of it through these means as well. All right. So, it is quite straightforward. We had the SHG second harmonic generation crystal here, the beams crossed paths, the outcoming signal at the second harmonic frequency is measured by the detector. One can use a lens to focus it onto the detector since the beam usually is divergent. One can also place a slit which lets only the second harmonic signal from the center pass through. This is essentially phase matching is done in the second harmonic crystal, phase matching about which we learned, and this is the active part of the detector, the rest is just the same old Michelson interferometer. So, one can then scan this delay and produce an intensity autocorrelation signal which is of the second order. All right, we can do that. So, that is how a second order autocorrelation is realized. So, a second order autocorrelation when performed, its histogram of points looks different from that of the first order. Okay. There is still a DC signal which is always present because both pulse 1 and pulse 2 can produce some amount of second harmonic by themselves. Of course, phase matching and things play a role, but you get a very interesting signal. One can show that it is like this. If this is the DC level, we have a signal below the DC level and we have a maximum of the signal above this DC level. Now, it is a rule of thumb, we can prove this rigorously, that if I take this to be 1 unit of the second order autocorrelation signal, then this on top is 8 units. So, we have an 8:1 ratio. In fact, in the laboratory, this immediately becomes a quick marker for the quality of the autocorrelation that we have achieved in an experimental scenario. Okay, we can have scenarios such as how good is the overlap of the two beams as we delay one of them with respect to other spatial alignment issues and things like that, right. So, if the overlap is very good, then you get the ratio of 8:1. Okay. Now, we essentially have two orders of autocorrelation which we have learnt how to realize, but then if you use only linear media, only first order is possible, and if you use time independent linear components using a slow detector, then we essentially have only the pulse, okay, and we will not fulfill the fundamental requirement of creating a shorter event than the event of interest to measure. Whereas, if you use optical nonlinearities, then we can produce something of a gate which is shorter than the pulse itself. So, this is the underlying reason why we use second harmonic generation. This point needs some elaboration and we will come to making this point in a much more emphatic way. In other words, if you do not have a detector or a modulator that is fast compared to the pulse width, you cannot measure the intensity and the phase of the pulse, which is the only thing you can do in a linear measurement, okay, such as a detector, interferometer or even a spectrometer, all of which are linear. But if you have non-linearity, then something else happens, Okay, you can get a signal, okay, with using the pulse to create a gate on itself using optical nonlinearities to do this thing precisely, that is have something shorter than the pulse of interest in order to calibrate the pulse of interest. So how is that done and what does that involve? So we will look at that. Some pioneering works are shared here from the group of Professor Ian Wormsley. Right now, before I proceed, I must make a statement of how good autocorrelation as a technique is. If we want to have a full knowledge of E of t, which is what pulse metrology is, then what we need in order to get a complete knowledge of the pulse, that is E of t, is to do higher and higher orders of autocorrelation. You need to extrapolate this to infinity, so to say. Okay, if we do this, then we can get a more and more complete knowledge of the electric field as a function of time, which is what knowing the pulse or pulse metrology is. But then the point is, higher orders of autocorrelation are successively weaker than each other, because every successive order of autocorrelation relies on a perturbative expansion of the type P P of, let us say, t is epsilon naught chi 1 E plus epsilon naught chi 2 E square plus epsilon naught chi 3 E cubed, and so on and so forth. And we of course know that chi 3 is numerically far less than chi 2, which is less than chi 1, merely because of the fact that this is a perturbative expansion. I should possibly write this as P of E and not P of t, although it is time dependent. Because it is perturbative, every successive chi for any medium in this perturbative regime turns out to be weaker, but here the interposing chi is chi 1, here the interposing chi is chi 2, here the interposing chi is chi n. So, your signal is essentially getting weaker as the order of autocorrelation increases. Okay. The signal is getting weaker while order of autocorrelation increases as we go down. They have this sort of reciprocal relationship, unfortunately. So, therefore, practically beyond a certain order, say even 3, it is very difficult to get autocorrelation signals, because the strength of E of t is itself limited. You have pulses, primary femtosecond pulses are nanojoule pulses with energies of nanojoules per pulse. You need to amplify them to get millijoules and whatever, but we want to have a technique which can characterize every pulse. Nanojoule, millijoule or joule is already a huge laser for that matter. So, that is where we are fixed, and up to third order is a reasonable ask in a laboratory. But what can we do better? We still do not have complete a knowledge as we may desire for E of t. We simply do not, although this is our stated goal. All you know and all you need to know is E of t, which you can say has two pieces, I of t and phi of t. One thing conspicuous by just a first look at our entire approaches, we have not addressed the question of having anything to do with phi of t so far? It seems we haven't bothered to pay that due attention. So that's something one should start doing, but let us understand even better what the problem with autocorrelation is. I will also have something more to say about it. In a few more slides to come. But what is the problem with autocorrelation apart from the fact that it places an extraordinary demand on the order of autocorrelation required for a more complete knowledge of the pulse? Can we not really live with low orders of autocorrelation, practically speaking? Or if we have means only for that, what would we be missing? This we ought to know this. Either we want a better solution, so we need to know what is the limitation with autocorrelation measurements of the type that we have mentioned here, first order, second order, third order, and so on. And what is missing? What am I missing in life? Right? Such a question. What am I missing with autocorrelation? What is autocorrelation? Let us look at that. Autocorrelation is the convolution of a function with itself. But what do we mean by convolution? A visual idea helps here a lot. Okay. If f is the function of interest, the function, when I say the function I want to know about, how would I know about a time varying function? How can I extract information? I take a known window function. The window function is something I know, it is a reference. F is this red curve over here. We have depicted all of these as Gaussians. Even a Gaussian, we need to know its width and everything else, right? So let us say I even know that the pulse that I am examining is close to, in temporal profile, to a Gaussian. I still need to know its width and whatever not. Then I take, if I had a reference like this whose width is even just a little shorter than the pulse itself, mathematically I can do this folding product where I take f, okay. Here the roles of t and tau are interchanged in this writing, so please excuse me on that. T performs the role of the delay here, not tau. So please watch out for this. T is the delay. I take the window function g, I have complete control over g. G is my reference. I somehow produced it. Say I have magically a pulse generator which can produce, say, attosecond pulses for me. I bought it off the shelf. Maybe in the future that will become possible. Then I cross reference my laser beam, my unknown pulse f of g with it, and I scan g, okay, over f. How do you do it in experiment? Blah blah. That's all there. I'm sweeping that under the carpet and saying yes, we can do it. If we can do it, then what's the consequence? I scan the window function over g over f, right, and I measure the product of these two. Okay, how do I do this? This is what we did in autocorrelation. In the interferometer we did this. We somehow interfered these two and produced an interference signal from the window function and the unknown function, and measured this with a slow detector, integral over infinity, scanning the window function g over the unknown function f. At each step I made this measurement. So this is nothing but the so called folding product or convolution. F star g of t, t being the delay, is this. This is convolution. Okay. Autocorrelation is a special case of convolution where f and g are both the same. Here we brought it upon ourselves, it is imposed on us because we have we do not have any other window function. But if you see this nice GIF, animated GIF shows us, which I did not make myself, essentially tells you that at every point the area under the curve of the product function f of tau multiplying g of t minus tau, the area under this product function is what this integral represents and it measures. Okay, it's the area of the overlap region. All right. So that is the convolution process. Is this specific to only ultra fast science? Do we have any other scenario where autocorrelation techniques are either known to be employed or are even forced upon us? Consider yourself to be a researcher on trying to figure out if there is extraterrestrial life and you are working on the SETI project. If you know about what the SETI project of NASA is, ETI stands for extraterrestrial information object or whatever. You want to detect if extraterrestrial life exists and if it's of a sufficiently advanced civilizational form, right, with a little less ego or little bit of humility, we can possibly presume that they are also fairly advanced and they send out some signals towards all of outer space with the same curiosity. Is there anyone else out there, right? If they do and we do capture that signal, and presumably that signal is electromagnetic because they are also at least as advanced as us, maybe we have reasons to believe they can be more advanced, and then say they are sending out signals intentionally or unintentionally. The earth is also beaming out signals with or without intention to communicate with satellites. Those signals will of course not easily die away in space and could be captured by some very intelligent civilization elsewhere, right. So if that is the case, how would we know whether this is signal from such an entity or it is just there is whole lot of electromagnetic background present in the universe? How would we know that this is the case, right? So maybe they send out some spikes of signals to communicate. It could be Gaussian, it could be pulsing with some encoded information. After all of optical fiber signals are encoded pulses and information encoded as pulses, but we have no reference to figure out this language except the sequence of pulses itself. We have no other reference. Therefore, to know whether this is signal from an from a civilization elsewhere or not, we have to use self-referencing techniques. This isn't science fiction. In fact, there is a very nice anecdotal episode in the history of astrophysics where this happened. If you look out, if you Google little green men and Jocelyn Bell, you would know that this is true history, right. Pulsars were discovered by Jocelyn Bell. Pulsars are pulsating radio sources and they emit periodic electromagnetic wave pulses, and these were captured by a giant telescope. This was in the radio frequency. There is GMRT, giant meter wave radio telescope, even also in India. So radio astronomy can be done from the ground, from terrestrial conditions. So they discovered that there are pulse sequences and immediately thought that this was a triumph of the extraterrestrial life project, right, that we indeed have figured out that there is extraterrestrial life out there. But of course, even before you can verify this, there would be a Hollywood movie or two on this concept, maybe even Bollywood these days. Very interesting. Of course, there have been a couple of Bollywood movies too, I think, right? It's called Krishna. No, I don't know, some other. Do you know the name of the movie? Which? Koi Mil Gaya. Okay. Very well. No limits to science fiction or fascinating writers like Asimov, right? Morlocks and Eloy, I think it is. Okay, whatever it is, there we essentially need our only way to understanding whether extraterrestrial life exists or not is autocorrelation. But it turned out later, and Jocelyn Bell figured out that these are pulsating radio sources. They are astrophysical objects, not due to an intelligent civilization. So we still need to, you know, go a lot, cover a lot of ground if we were to fulfill the Drake equation for figuring out extraterrestrial life. So, but the key is only autocorrelation is our only hope there, but for a very different reason. We don't have any other reference. We don't know their language. Do they use Morse code, whatever? We don't know. Likewise, other way around, right? But there is a very interesting thing in linguistics which I came across. I will not elaborate too much. For those of you who are aware, maybe archaeology aficionados or history buffs. So these 4 tablets over here are essentially excavated pieces from the Indus civilization, Indus Valley civilization, Harappa, Mohenjo-daro and places like that. Basically the question is, these are symbols. You have caricatures of a bull, of a human being, and what looks to be like a cow or a horse or whatever, maybe it's a cow, whatever animal, and you have some inscriptions on top here, right? Are these inscriptions just symbols of objects like a fish and whatever else here? Are these just pictorial depictions like cave paintings, or do these constitute a written language? Do we know if this is a language? Then we know that a language like English exists, we speak it, but then my mother tongue, my native language is Tamil here. I may have learnt some Sanskrit at school. So I know these 3 languages because in principle I can translate the same information between these 3. That's as far as my linguistic knowledge goes. I may know one a lot more than the others. I may be more comfortable in one than the other, which is probably say English, right, or equally maybe to some extent Tamil. But then there could be a language like Fortran, which is a computer programming language. I understand the code in Fortran because I interpret this or I parse it into English and assimilate the information. So translation, intertranslation is the key. So ancient Egyptian language essentially was made up of hieroglyphics, as they call it. I hope I can even spell it right. For a long time we did not know about whether these characters painted or found in pyramids constituted a language until a Rosetta Stone was found, which essentially was a tablet where the same information was written in the unknown language and a known language. I think the known language here also happens to be something ancient Greek, and the unknown language, the same information was present, and then people could figure out based on that. So you start learning a new language. Now with this kind of caricaturing, how would we know whether something constitutes a language or not? You have very limited information, that is these four tablets. So this was essentially a problem, scientific problem solved in the early 2000s by a group involving a group of researchers from a computer scientist, computer science group from Washington State University led by Rahul Rao, and also colleagues from this very city, Chennai. You need expertise in computer science and linguistics. The linguist of interest here was Airavatham Mahadevan. He is an exponent of ancient linguistics. Actually, I think he lives in Chennai, this city. So they worked together to plot the sequence of a block and the entropy, a measure of disorder, a kind of entropy, where while I don't understand all the math and computer science, it's very nice and easy to read off this chart, which says that as the length of a sequence of the blocks increases, Then a computer language, which is a very ordered set of characters and words, because you do not want to make syntax errors in a programming language. This is about the one of the most ordered sequences you get, right. Whereas zero entropy, zero disorder is a keyboard stuck maybe on the letter A, that is zero entropy, that is the line here, right. So, you take characters without telling the computer as to whether this constitutes a knowledge or a language or not, and ask it to figure out and measure the entropy. You do this for various things, a language like Fortran, Sumer, a language, the Indus Valley script is the blue curve, and then you see there is English somewhere, English words, characters, there is Sanskrit, there is Tamil, there is even music written, right. So, you do that, and you even take DNA and protein, and all these are DNA is code. Code is again codification, it is a kind of language, right. Now, the discovery of this work is that without any prejudice, when you carried out this exercise, the Indus tablets, their entropy fell within the range of normal languages, and they figured out that this constitutes a language. I mean, this to me is a beautiful example of a kind of autocorrelation technique. You squeeze out a measure from whatever orders of autocorrelation. Obviously, here the signal is two dimensional. The pulse with a variable of just t is one dimensional. So, this is a two dimensional problem of retrieval of information from using a technique in a scenario where we do not have anything but just one piece of the signal itself. Okay. So, it so turns out that one of the tablets here apparently read a Tamil phrase Elumin, which means 7 fish. This could be figured out from reading this tablet, and it was proven that the Indus symbols here actually constituted a language. So, it's these sort of self-referencing autocorrelation techniques abound various fields of research, as they do in ultrafast science too.